Today on the podcast, we have Dr. Amaury Triaud, who's at the University of Birmingham, and he is an astronomer who focuses on exoplanets and planetary formations.
First part of the conversation, we heard about his recent trip to Antarctica, and it was really fascinating just picking his brain about what it's like to actually work and live in Antarctica, and what's the point? Why do they have to do that? What are the possible benefits, particularly cost benefits, of doing research down there, even though it's extremely cold and difficult to get to? So that was kind of mind-bending. Then we talked about how exoplanetary science is really revolutionizing our ideas about planetary formation in light of the fact that we spent, 300 years thinking that all solar systems would be just like ours, and it turns out it couldn't be farther from the truth. And then finally, we unpacked his latest two Nature papers, which concern, one, these groups of planets that are living around two stars, a binary pair, which is very bizarre, and nobody thought that was going to happen. And secondly, the apparent dichotomy between carbon dioxide worlds and water worlds, and what that tells us about a continuum between the two and planetary evolution. So it was a really diverse conversation, but really clarified a lot of my ideas, and particularly in terms of slotting in some of the very bizarre discoveries that are coming, that we see headlines about, these co-orbiting Jupiter planets with no star associated with them in the Orion Nebula. Just strange things that are happening that are really forcing us to rethink planetary formation. So, it's a great conversation.
If you like what we do at the Demystify Sci podcast, consider coming over to patreon.com and donating a couple dollars a month so we can keep the ship going. A couple dollars does not mean that much when it comes from just a single person, but through the power of large numbers, we can make this something that we never put advertisements on, that we never have to get some kind of sponsor for, where the editorial content will always remain independent and will always be informed by what viewers like you enjoy.
In other words, we can study what we want. No one's going to tell us what to do. If you also want to support the podcast, consider coming out to this conference. We're having our first Demystify Sci live event in Austin this April, the 7th and 8th. It's going to be super epic. We're finally locking down the speaker list. It's amazing. Michael Levin just agreed to come and give a presentation.
Remotely,
it's going to be a nice Q&A session. So I think the huge benefit of coming together in person is that we can actually field questions in real time. We can interact, not just us, but you guys can interact with the speakers and the guests, and we can sit around and brainstorm. We can hang out in the evenings. It's going to be a really intimate and awesome setting, and I'm really excited to see you there. Grab your tickets while they're still left up here, and I want to see you out there in Austin.
Indeed.
All right, let's get to the conversation and see what's going on with planetary formation these days.
The scientific revolution starts now.
Demystify Sci podcast.
Let us see in the dark.
Now, so you just returned from some pretty epic expedition. Is that correct?
Yeah, I was in Antarctica. I left the UK for about 2 months. Overall, it was extraordinary in many, many different ways. I'm really glad I went.
What was the purpose of your trip?
We were changing or upgrading the hardware of one of our telescopes there, changing notably the motors that are driving the telescope, because after 10 years of Antarctic service, the cogs, so in Antarctica, temperature changes quite a lot, quite dramatically sometimes. And so all that has a big wear and tear on materials. And we were changing it to a new technology, which then doesn't have those cogs. So then at the moment we had game on the old cogs, but now we have engines that work as motors do normally with electromagnetic coils, and so there's no contact anymore, and that should work better.
Is it dusty down there? What happens to the machinery?
No dust. Just there's actually that's remarkably clean because there's only ice. We had in a 1,200 kilometers from the sea, in the center of the continent. So there's only ice, and even ice, it's so cold that it behaves a bit like sand, and you can blow it, so it doesn't really accumulate, or it doesn't do anything like in the US, for instance, when you see the the snowstorms. And it really is just the fact that it gets really cold. It gets down to minus 80 degrees Celsius. I don't know how much it is in Fahrenheit. And sometimes we have changes of 50 degrees in one day. So it's a huge change. So it's nearly a change of 100 Fahrenheit in one day. And so that has massive impact on machinery and its longevity.
Interesting. And why do you need to be at the South Pole for this kind of work?
You don't need, but if you're there, you have an advantage. The most immediate is that during winter, austral winter, you have a nearly continuous night. So you get the advantage of observing from space, but without having to launch a rocket. So that's quite good. The other is that because we are already at 3 kilometers in altitude, so below us is about 3 kilometers of ice. And then because we're near the pole, the atmosphere is a bit more compact because the gravity is a little stronger. And it's also cold, so the atmosphere is more compact. And so it means that we are the equivalent of 4,000 meters. So that's probably about 12,000 feet. So it makes it one of the highest observatories in the world. And you see stars clearer if there is less atmosphere. And in addition, it's also by far the driest place on Earth. So we get 10 times less. We have 10 times less water in the atmosphere than in the driest desert elsewhere on Earth. So we see very clearly the sky.
Is water one of the biggest factors in terms of distortion when it comes to the atmosphere?
Yes, it is. Yeah, water vapor is one of the largest, especially for someone like me when we're trying to find water on other planets. The water in the atmosphere of our own planet actually prevents us from seeing the water in the other planets. So it's an issue.
And what are the key wavelengths? Are you looking in the radio frequency, or where are you looking mostly?
At the moment, our telescope is purely optical wavelengths. Although the way that we call optical is a little strange because some of those optical wavelengths we don't see with our eye. They would be called near infrared for biologists. But as physicists, we determine that more on the technology that we use to observe. But we have plans to go into the real infrared because the cold temperature mean also. So when you observe in the infrared, everything becomes noisy because like the temperature of the Earth, the temperature of the telescope itself creates light in the infrared, and so blurs the sky. But then if you go into a very cold site, then you get a sky that is also very dark in the infrared. So that's the next chapter, I guess.
How many other telescopes are down there?
At the sites. Sorry?
Is it just a huge array with a bunch of different projects? Are people sharing telescopes, or how does it work?
No, there isn't much at the moment. So there are 2 telescopes at the site that I'm going. It's a Franco-Italian base called Concordia. We have a 40 centimeter mirror telescope, and the Italians have an 80 centimeter, which is not quite working at the moment, but they're working hard on it. And both telescopes are meant to observe in the optical and infrared. At the South Pole, there is an American base, and there they have what we call the South Pole telescope, and they observe more into the radio waves, so millimeter waves. Also using the fact that the atmosphere is very dry and very cold, but they have very different projects. But we don't have much astronomy in Antarctica. It's actually one of my aim is to increase a bit how much we're doing there, because it really is. It would be the best observatory in the world if it was developed and had a larger infrastructure.
What keeps it from having larger infrastructure? Because I know that there's like a decent amount of bases and countries that have established themselves down there.
Well, the logistics is difficult to begin with. When you're going there, the power, the limitation of power is also very limited. So when you're there, we're 1,200 kilometers from the sea. It takes 10 days for a caravan to get there. And you can only have 3 rotations to 4 rotations of the caravan per year. And most of what is brought up is oil to warm ourselves, but also food, canned goods mainly, and then spare parts. All this is far more important than any new thing. And then you can add some of the new stuff. So the logistic is really difficult. And before you bring it from the coast, you need to bring it to the coast. And there again, you have only 3 or 4 rotations by boat per season that are possible, where the ice allows you to approach the continent and actually take away the cargo from the cargo bay. Actually, I would say there's probably less than 3 rotations where you can really do that in any practical way. And so that limits you as well. But because you need a harbor, then the boat is also filled with, food and oil for that coastal base. So the logistics are particularly complex. In Concordia, we burn something like 300 cubic meters of oil every year to warm the place and power everything. And for every liter of oil that you bring, you need to burn 1 liter of oil to bring it there. So it's really a consumption of about 600 cubic meters. And that limits things quite tightly. You see it; it's very tangible, because when you see the caravan arrive, a third of what there is oil, and we feel a little bad because it pollutes not just the air but also the ice around. But there is no other way, to survive there. It's a world where we're really not meant to be. It's a desolation as pure as you will ever see. It was actually, even though people had told me about it, it kind of took me to the heart a little bit, because there is absolutely nothing. There is no noise. There is no smell. There is, when you lift a book or if you leave your luggage in a corner of the room, you will never find a cobweb, because there is no insect. There won't be a single fly. It's even hard to make bread because there is no yeast in the air. Like, there is nothing. It's weird to experience nothing. And where we are, the ice is also so flat. So you're on a glacier, and it's so flat, it's impossibly flat, like the sea, but nothing moves. So it's completely static. It's really weird to look at nothing. It's I know the people that told me that it was like that, and I told me a bit what to expect. It really dawns on you when you're there that you've really reached the end, in a way, a place where there is no life, and there is no smell, because there is no earth, notably. There is no remnants of biology anywhere. The only things that are alive are humans and I guess the biome that we bring with us.
Can you go outside? Like, can you get some exercise? Is there any, expeditions just to see what's happening?
Day trips?
Day trips, yeah.
So no, you can, as a tourist, get to the coast. Those expeditions are a bit controversial for scientists, because usually the tourist ships get to want to see colonies of penguins, and those are quite fragile. So this year, for the first time, there is, for instance, avian flu in Antarctica, which is causing some havoc in some of the colonies. But to the center of the continent, it's almost impossible to get to. There is no, you would have to go through the polar agencies. So you need to have a good reason to go there. So you might go, for instance, for a documentary, or as a journalist. We see some as a tourist, just to see the sights. No, it's just, it's difficult enough as it is. It would be hard to, and hard also to explain to people locally, because when you live there, you live in a community. It's very Monaco in a way. Like, you eat 3 times a day with the same people. You are constantly with people, sharing space with people, and that forms very tight and very strong bonds very, very rapidly. And so bringing an interloper just for 2 days to just look around, it's just strange. What are they doing?
But what about you guys though? Can you guys go outside? Do you spend any time out on the plane there?
So outside, yes, you can go. It's not too cold. Where I was, it was minus 35 to minus 30 degrees C. When there was because of the wind, it was the equivalent of minus 45 to minus 50. Feel temperature. And as soon as you put your polar gear, you feel good outside. After a few hours, you will start feeling cold in the extremities. But beside, you're well protected, and you can go, and you get used to it. One of the things that I was surprised, even though I knew that humans are very adaptable, is how easily we adapt to new situations. So, for instance, the life in a community, the life, or rather the the routine of wearing your polar gear to go out, walk, and then strip some when you go into another shelter, and what you bring back or what you do, but also how you adapt to, say, when I took the boat to come back, it was a French military boat. There is a new community on board, and you spend 10 days with these people, and it's yet another place where you adapt, and then you adapt to the constantly moving environment this time, whereas it was completely static before. Suddenly you have a new environment which is completely moving. Also, something that was odd is while it was complete daylight, so there was no night for nearly 5 weeks while I was there, and then the first night or the first obscurity that happened when it was on the boat when we left the Antarctic Circle. I woke up during the night and I was a little lost. Like suddenly it was dark and I was like, "What? How am I going to the bathroom now?" And so I had adapted to something for which I didn't think would be so easy to adapt. You need to adapt to the altitude. You need to adapt to so many things, and the body keeps adapting, and it's remarkable. And it's part of some of the things that are extraordinary and why I loved going there, because you realize that about yourself, how you adapt to the altitude, to the cold, to people, and then you keep doing that, and then there's always something new happening, and it's quite reviving in many ways.
Yeah, I mean, I think that that's the foundational principle behind travel, right? And travel as it is now, where you go along some tourist circuit where you end up in these places and there's the list of the places you have to go is deeply unsatisfying. But travel with a purpose where you're like, I'm going to fix a telescope and I'm going to this place and there's a mission and we are all here under the guise of a goal that we share is really meaningful. And I think that that's maybe one of the coolest things about these sorts of expeditions.
Yeah, you're totally right. I think I've told that to people, on the fact that we had a purpose and we all believed why we were there and all shared why we were there. Like there were different scientific missions with different goals, and that was really, really good. And, in addition, you're really focused on it, and because you barely have internet. So I did not know what was going on in the world. When I came back to the UK, I did not know if our prime minister was still prime minister, for instance, and I couldn't care less while I was there. I didn't receive emails, and that was also a liberation from daily life, daily routine, and a constant bombardment that you can get either from colleagues or from 24-hour news about stuff that you need to pay attention to. There was one goal. We needed to do this, and then we needed to live together. And that clarifies things, and that was also very liberating.
Go ahead.
I was going to say, did it free up any time in your mind to think about the scientific ideas that underpin a lot of these engineering projects? The actual interpretive side of what you've been seeing in the sky over the last 10 years of your career?
It's a good question.
It's funny you ask. So often when I go to places, or I've been to observatories, and like when you have this time to yourself, you do think about why you're there. And I often have my better ideas when I'm at those places. So I like going, even though, going to Chile or going to Antarctica takes a lot of time and a lot of resources, and you wish not to use our planet that way necessarily. Being there does put you, in a situation where you have time to think of why we're doing it. And I've always loved that. And while I was in Antarctica, I did think not about the interpretation of our data, but what else could we do? And seeing the site and understanding the logistics and what could be done, what could not be done, I started thinking, well, if we were to build a bigger telescope, what does it mean compared to other telescopes elsewhere? And I was just confirming that with a colleague a few days ago. And by our recollection, something we need to confirm, a telescope that would be 2 meters in diameter would be able to would have the same power to discover than a telescope that has a mirror of 8 meters. Now, one of those telescopes, or some of the biggest telescopes in the world, they cost between $1/3 and $500 million to construct. But a 2-meter telescope costs 10 million to construct. And so for a relatively small infrastructure in Antarctica would have like a power to really observe the sky in ways that we wouldn't be able to, that we are able to otherwise elsewhere, but where, because of the unique pressure, everybody wants to access these facilities, and we don't have time to do everything. And so by having that one telescope way cheaper, then we would get the time to do what we want. And so that trip was very instructive for that purpose, because it gives me, now a new idea, something to push, a new project to think about, see whether it is indeed what I'm saying to you now, whether we can physically do it, because when you request money, say from a research council, it's only for a certain time, and so you need to construct by a certain time. But Antarctica comes with its own sets of challenges. You can only build for a month and a half, because otherwise it's too cold. So you have to get there in November, mid-November, something like that, and you have to leave, like by mid-January, and there is nothing you can do about it. So it limits you, but we'll see.
I didn't totally follow that. So is the 2-meter telescope as powerful as the 8-meter because of its location? Are you comparing it to one that's located, say, at higher latitudes or something? Or
yeah, so it would be, you're right to ask. Yeah, this 2-meter, because of the location of Antarctica and the conditions in the sky, would have the same detection power as a telescope in Chile, in one of the best sites in the world.
Gotcha.
So it's a way to show how good of a place Antarctica is for astronomy, but also how hard everything needs to be warmed constantly, because otherwise it's too cold. When you go below minus 50 degrees, a lot of electronics don't work. Plastics don't work. We need to use special tape even to just tape stuff, because otherwise it doesn't stick or it becomes brittle like glass. It's really a weird place. So there are unique challenges. But if you manage to construct that, if you manage to overcome the logistics and the issue of creating enough power, electricity on site, then you have one of the most powerful observatory that you can build would be there.
I've been reading this book, slowly making my way through it, called The Power Broker, which is about this guy named Robert Moses, who was the director of the Parks Department in New York City from the 30s through the 60s. And he's widely renowned as being somebody who was able to build things that no one else was capable of building. And I mean, he was a little bit psychopathic in the sense that he was completely motivated by power, but he had this really interesting way of going about projects that he knew no one else could build, where he was like, you have to drive a wedge. And what you do is you start a project, you get funding for it somewhere, less funding than you can possibly use to build the entire thing. And then you build the foundation of whatever it is, like a highway, a park, or something. And then you publicize it because the people really want it, because in New York, everybody wanted parks. And then when the money runs out, you go to the administration and you're like, well, we've already started. Are you going to let it go? And he was fantastically capable. At some point, he was able to generate enough money off of like tolls on his bridges and things like that, where he didn't have to do that anymore. But in the early days, that was the process by which he ran it, because it was never possible to get enough lump sum to be able to build like an entire highway. And the funny thing is that you have to look back on his legacy and question whether or not what he built was a good idea or not. And so there's like a little bit of that. But I feel like there's something to be gained from the approach, which is that when you're trying to build something extraordinarily just complex and expensive, that there's just this, if you drive the wedge, then you can probably finish it.
Okay, interesting idea. I don't know if that exactly works with our process of funding, but I'll see what we can do. It is something that suits America better than Europe. I know, like, for instance, there's a huge telescope under construction in Chile on a mountain called Las Campanas. And it's run notably, I think, by the Carnegie Institution. And there then didn't have the whole funding to start building. But as soon as they got a bit of money, they started, creating the foundation, like you said. Then they got a bit of money, and then they needed to. So it's not, instead of a telescope with one mirror, it has something like 7 mirrors or something like that. And they built one mirror, or they bought one, knowing it was useless on its own, but that's the money they had, and then progressively raised it like that. A few kilometers further north, 400, 600 kilometers further north, there is the European equivalent. But for that, we needed to have the whole budget to start construction, because otherwise you end up with that issue that you were describing, that it's not finished. Therefore, we need to invest more, and that's a good way to let cost overruns happen. So it's a different strategy or different philosophy to approach it. But I'll keep it in mind. I don't know if that's possible on our side, but if we can do something, progressively, like or buy one part of the telescope in one pot of money, one research funding pot of money, and then another part in another, it might happen that way. But certainly, I think we need to convince that it's worth doing, and not just the research agencies, the polar agency as well, because they need to know that it's worth building capacity and taking room in the caravan to bring our stuff there, that it's worth keeping the base, etc. So it's a lot of people, but I think we're in a good way.
What is the polar agency? You've mentioned it a couple of times now.
That one was the French Polar Agency. There is a US Polar Agency. It's just the agency that takes care of organizing things. So the French Polar Agency doesn't do science. It's an agency that enables science. And what it does is ensure that there is food and oil in the various bases. It ensures that there is technical staff there, because when you need to build, you need builders. So you need an electrician, you need a plumber, you need carpenters, you need electronicians, and all these people, we don't have in our research teams. So the agency hires those people to enable science, and then we have to see whether they have time for us. And so that's why we need to convince them also. They need drivers for the tractors that are bringing everything in. We need sailors. We need cooks. There's plenty of jobs. And actually, I tell people, if you want an adventure, do look at your own country's polar agency, because every job is kind of needed down there. And so, if you want a strange life for a few months up to a year, that's one option.
Yeah, it's a very romantic notion, and significantly less likely that you're gonna, freeze to death eating seal blubber at this point.
Okay, great. So I was hoping we could shift gears a little bit and talk about the science underpinning the purpose for a lot of this research, because honestly, I think the topics that you're studying, exoplanetary science and really planetary formation, are some of the fastest changing sciences on the planet right now. And they're really exciting as a kind of test case in how fast our understanding of nature can change. Most of modern science, since even really Galileo's time, if you call Galileo the first scientist, we pretty much thought about our own solar system as the test case. Like it was an n=1 situation. And when we tried to imagine how the solar system formed, we were looking at only our solar system. But now that we're able to see other solar systems in various stages of their lives, it seems to be really rewriting the game. And so you sent us a couple of papers that we had a chance to check out. And I definitely want to talk about those. One specifically about identifying water-like terrestrial planets, and the other about these planetary systems that are orbiting more than one star at once, which is, of course, something nobody would have thought about looking at just our own solar system. But there's so many other things, and I'm wondering if you can maybe situate us with some of the biggest changes that have occurred in the last 5 or 10 years with regard to our ideas about the solar system and solar systems in general, things that we would have never thought possible even just 10, 20 years ago.
Yeah, sure. I can also go back a little older than that. So interestingly, when you look at Greek philosophy, people had imagined that there would be other worlds. The one thing that they had not realized is that a planet and a world are the same thing. So planets for the Greeks were moving stars. For us, it is now a world. We now know that the planets of our solar system are not moving stars, they're worlds. And that is actually Galileo that found that out. So in one observation, he observed in the telescope Venus and solved the problem that the antique philosophers had a huge trouble with, which was why was the planet Venus as like a moving star changing so much in brightness compared to anything else. And the reason why it does that is because, like the moon, it has a crescent, and sometimes we see a tiny crescent, and sometimes we see it nearly full. And sometimes it's further away, and sometimes it's closer because of its path on its orbit and the position of the Earth relative to that. And so Galileo, in one observation, realized that planets were worlds, and therefore that our world must be a planet. Like our Earth was not considered a planet before. And so when you read ancient literature, world and planet were completely different, but now we like those two words are equivalent.
Hey folks, just a quick interruption to let you know that we absolutely depend on listener support to make this project happen, to give more and more time to it, and to ratchet up the production level for this show. Spend more time finding the guests that we all want to hear from, and we need your help, so please come over to patreon.com and join our community. We get together once a week, have a roundtable discussion. It's a really, really special environment, and you can come and join us for a donation of as little as a couple dollars a month. So, see you there, and here's the link.
So that was one of the first concepts that was established. The other thing that is very clear is that the unique source of light is the sun at the center of the system, and it illuminates the worlds and the planets. And the other thing that was interesting was that then the Earth had to orbit the sun because of that observation. So we had ideas, from ancient Greece, but also, northern India, that maybe the sun was at the center, but there had been no proof. Now Galileo was proving it. And because the Earth is moving around the sun, then it has a parallax effect. So when you look at stars on this side of the orbit compared to this side of the orbit, you should see stars move a little bit relative to one another. But because no one had ever measured that motion, that's why most people thought the Earth was static and at the center of the universe. But suddenly, by proving that the Earth must be moving by observing Venus, then because the Earth moves, then the parallax must happen. And the reason why the stars don't show that motion must be because they are extraordinarily far away. And so in one observation, Galileo expanded the universe dramatically. And that was the birth of astronomy, because then if, so much of it is empty, like what is there, it's a huge place. So if you move a little further in time, closer to us, then people went back to Greek philosophy and wondered, well, there must be planets around the stars as well. And so, many people were imagining that there were an impossible number and an infinite number of planets in infinite numbers of shapes and configurations and all that. And then you reach the birth of spectroscopy in astronomy around the 19th century, where people were able to measure the spectrum of a star. So that's how light or the amount of light changes with wavelength or color. And then we're noticing that many of the stars were rotating really fast, but the sun was rotating really slow. And that meant that those stars had a lot of angular momentum and our sun didn't. And in a solar system, there is this quantity in physics called angular momentum that you cannot dissipate. You can only put it, give it to some other body. So you cannot destroy it. You cannot get rid of it. But in a solar system, most of the angular momentum is in the planets. And so the idea was at the time that, okay, the stars rotate fast, they have a lot of angular momentum, therefore they must not have planets. And our sun has no angular momentum, it rotates slow, and the angular momentum is in the planet. And so by watching all of the stars rotating so fast, then up to about shortly before the Second World War, most people thought there was only one planetary system in our galaxy, just because the stars rotated fast. What they didn't quite realize at the time, I believe that's what it is that first the sun used to rotate really fast. And the fact that a star rotates fast doesn't prevent angular momentum to be stored in the planets, but also that many stars rotate slow. It's just that their instruments weren't able to measure it. And so the only one that they could measure were the bright, fast rotating stars that we also now know, also the one that are less propitious to have planets for other reasons, because they're very short-lived, they emit a lot of radiation and other things. But from the moment that you realize that angular momentum problem, you go from people thinking there was only one planetary system in a galaxy to every star must have planetary system around about 1940s. And then the question was, where are they? And you start having people and you start having reports in the scientific literature of people claiming they've discovered planets, except that each of those were then turned down. They had not. There was a mistake in the measurements. Until, that is, you reach the mid-1990s, where the first exoplanets are detected. And at that point, what most people expected were copies of the solar system, like what you were saying, Shiloh. They were expecting a star and then maybe a dusting of small planets close to the star and then large planets really far away, like Jupiter, Saturn, Uranus, and Neptune. And so it was a bit of a surprise when the first planet around a sun-like star was discovered. It was a gas giant, like Jupiter, very much like Jupiter, but turning around the star in only 4 days. And we now refer to these as hot Jupiters. And so it was where people thought planets like of this type should not exist and should not be there. And pretty much everything that we've discovered so far has been where it wasn't predicted to be early on. So at the very beginning of my PhD thesis, there was a big paper also showing that there should be very few planets between the mass of Saturn and the mass of the Earth, very close to a star. But it turns out that the largest population of planets has a mass between Earth and Saturn and is close to the star. So even with exoplanets being discovered, and here now we're around the mid 2000s, people were still making predictions, and exoplanetary observation kept defying those predictions and showing something else. What this shows is not that the physics was wrong about planet formation in the solar system, but more that it was incomplete, that some aspects of it were not perceived to be important because they seem to have played no role in appearance in the solar system. And now a key question is, why didn't those physical processes play more of a role in the solar system? So in 30 years, over 30 years of discovering exoplanets, I think the biggest discovery that we have is the diversity, that worlds are really, really diverse, almost like what the Greeks were discovering, or saying, not discovering, an infinite number of planetary architectures and shapes and things like this. But this is weird as a physicist, because what we learn when we do science is not everything is possible. Not everything is strictly possible. That's why we have a natural law. For instance, an apple will never go upwards, unless you assist it, say with, a rotor or you put energy into it, but it will not. And that's because gravity takes over that. Similarly, all of the physical laws restrict effectively the domain of possibilities. But in exoplanets, it seems like a lot is possible. And so now we have a very interesting job of finding what physical laws underpin all of that diversity. It's very hard to explain a very diverse population with one law, and yet we hope and we think that there must be one, because ultimately there is physics behind it. Some dust must accumulate to become a planet, and we know that's a physical thing, so it must follow some physical rule. Now it's which one apply, and once we have such laws, then to see whether we can actually make sound prediction, and therefore that will become then a new theory.
Now, there's a number of ways to, say, build a house or to build a car. I mean, there's probably some conserved aspects, but I assume you could, build it on an assembly line. You could have people in different rooms building the individual parts and then bring it all together at the end, right? There's in some sense conserved processes and diverse processes going into it. Is there a sense that there might be more than one way to form a solar system?
There are a few pathways, yeah. So the leading theory is what we call core accretion. So dust accumulates in something a bit larger, and then that dust accumulates in something yet larger. And eventually you reach something like about the size of, the Earth, or something like about 5 to 10 times the mass of the Earth. And then if you reach that threshold, then gas will spontaneously accumulate on your planet if you're within a gas disk. And that's the leading idea behind the formation of the solar system. But you could have an alternate scenario, is that the planet formed by what we call direct gravitational collapse, a bit like a star. So if you have a disk around a star, so the disk around the star is, again, due to that angular momentum thing that we were doing. But if the disk is massive enough and not too hot, quite cold, then at some point it will start fragmenting. And it will create a lump, and that lump can create a planet if it's not destroyed by perturbation in a disk. So that's another scenario. We think that scenario is much less likely, and it tends to work mostly at large distances from the star. So it makes it hard to explain planets close to the star and small planets. And then recently there's been a sort of, refinement of core accretion called pebble accretion, where instead of making things, from small to a bit less small, to medium, to a bit less medium, to large, to planet, to big planet, that actually most of it happens with pebbles, so sort of rocks that we could almost hold in our hands. But those rocks are free flowing around the star, following their orbits. And at some point, in a sort of mixture of gravitational collapse and local forces acting on them, like for instance, if you have one cyclist or one bird, they have to go against the wind on their own. But if you have more than one, they can go against the wind a bit better. And so if you put that in the context of a planetary system, you have one pebble, going against the wind, so to speak, of the gas in the disk. Then the one that will be behind will go a little faster because it doesn't have to go against the wind. And so it accumulates. And then at some point you have enough material that then it gravitationally forms an object. And then pebble accretion has other interest in that it brings a lot of material from far in the disk into the inner part near the star and gives therefore a lot more chances for planets to be created over there. But those flavors are there, and several processes might happen. I think what's also important is that several processes can happen after the planet formation process. So I think a big idea around the time that the first exoplanets were detected that was shattered was that the solar system is a safe place. We think of the solar system as stable, but in the 90s, somebody calculated that there is 1% chance for Venus to be ejected out of the solar system in the next billion years. And now the idea of exoplanetary system is you actually create lots of planets in your system and progressively you lose them because of dynamical interactions. One of the planets will just be kicked out of the system progressively, preferably starting with a small one. But it brings an idea of planetary system which is far more dynamical than we thought, where we think star forms, disks forms, planets form in a disk, and that's it. And then life appears and everything is good. It means that even after the formation of the system, there's still things happening, that interactions between the planet can sculpt, can lead to collisions. The moon is probably one of the last collisions that happened in the solar system, creating the moon. Some planets can disappear out of that. And so it shapes things and changes things. And what we see nowadays is the result of all of these processes together. And so it means that it can be hard to know which of these processes has happened because many of them have happened. And some of them are quite, stochastic, random in nature, like orbital interactions. So deterministic in some way, but very hard to calculate. And so by all intent and purposes, they follow chaos theory, and so they appear as random.
I wonder, there was a really weird Quanta article the other day about findings that the James Webb had made. I think it was in the Orion Nebula, but I can't remember exactly, where they had found these pairs of Jupiter-sized planets that were orbiting each other.
Yes, you're right. And I've been fascinated by that as well. That came very left field. Again, another discovery. And that's the thing that as an astronomer, I wish I had observed. I'm an observer. I want to find cool stuff. And that stuff is darn cool. It's so, as if my recollection is right, they call them JUMBO, so it's Jupiter mass binary objects. And they were looking for those sort of gravitationally collapsed objects, so that planets that would have formed like stars, but a bit differently from what I just described to you. They were trying to find them isolated. Like, so some stars form, and you might think that, say, a star or the gas that would lead to a star starts collapsing, starts creating something a bit dense at the center, and if something bad happens, like supernova nearby, it blows most of the gas out, and then you're left with something very small, for instance, and it could become planetary size. Or through some combination, some smaller cloud could happen. Low probability, but eventually, because of the sheer number of things that exist, you would detect some. And they were looking for those. And they found those. So that was great. That was a great insight. They were looking for that. What was the real surprise is that they found them in pairs. And that was really weird. And in pairs that were not really close to one another, but rather large, which implied that they had formed together, but somehow had not been ejected from something else, because the chance of ejecting an object is already low, but to eject two and they remain bound together gravitationally feels very far-fetched, although some people are now working on testing that hypothesis, because it was, at the time, I think, a suspicion that the researchers had, and so that needs to be tested as a scenario as well. But it seemed too many for luck or for that process to happen. So they're very exciting objects. I think it brings something new, and we'll see how much they affect planet formation or whether they actually affect stellar formation. It might actually be something more interesting for stellar formation and planet formation, but we will see about that. But yeah, it was exciting.
Is there any sense that an object that's formed along, let's say, a stellar formation pathway would be able to have sufficient metal in it to form the kind of molten core that a planet has?
So here you're talking more of an Earth-like planet, a rocky planet, right?
Well, I'm thinking, is it possible to have something that's Jupiter mass with a core that is Earth density?
Well, that's a good question. You should start a PhD, maybe. It's a big question. For instance, for a very long time, we did not know the core mass of Jupiter. So at the moment, there's a spacecraft orbiting Jupiter in order to measure precisely that, because the idea was that it should have a core mass between 5 and 10 times the mass of the Earth. I don't know actually what their results are at the moment, but I do think that they've managed to measure the core of Jupiter, and that it was smaller than anticipated, if I recall well, although that would need to be checked, or less massive. Now, I don't know. I'm not the type of person that does planetary interiors for this kind of gas giants. And I don't know whether the core there is expected to be molten. I don't know if it's expected to be hot. I suspect there should be some residual heat from formation, because it's hard to escape because of the layer of gas. But I don't know if it's molten, or if, because of the sheer pressure of gas on top, whether it has another phase of matter.
And the composition, too, is a little bit up for grabs from what I can tell, right? Because I think Anastasia is talking about similar elements, these nickel iron base that we have on Earth. But, Jupiter seems to be mostly hydrogen. It's very similar to a star, I guess, hydrogen and helium. And so there, for a while, was talk of maybe some sort of new phase of hydrogen, like a liquid metal type phase at the core.
Yeah, so it would have been at a transition above the core. I think the core is still thought to be of made of what we in astronomy call metals. So it's everything else that is not hydrogen or helium, and primarily would have been made of silicates and ice, water ice, because the idea is that you have a star, and then at a certain distance, within a certain distance, water is in the form of vapor, and further than that distance, water would exist in the form of ice. And in the form of ice, it means that you have a building block to construct a larger body. So, for instance, it's very hard to keep gas on a small object. For instance, Mars is already barely keeping its atmosphere, and we still think of it as, a bona fide planet. In practice, it might be closer to an embryo, but we'll leave that debate for another day. So attracting gas, is difficult. And so to build something large, it's convenient to have water in the form of ice, because it increases the building materials. And the thought is that the cores of the gas giant planets are made mostly of silicates and ices. So either water ice if you're a little closer to the star, or CO2 ice if you're a little further, or CO ice if you're even further, etc., etc. And that on top, then you have a huge layer of hydrogen and helium, but at the base you would have silicates and probably some nickel and iron and things like this as well, because they would be brought with the rest of the rocks.
Did you have a line that you were pursuing with it? I didn't mean to derail you, but you asked about the possibility of these Earth-like cores inside of these binary Jupiters.
I mean, just in terms of what we were talking about earlier with the multiple paths towards forming the same sort of structure, where I've always wondered if aborted stellar formation isn't a plausible path towards a rocky planet. And I feel like the theory that says that that's not possible is that star formation doesn't accumulate enough metallic substances to create a core, and so you'd have to have something that's enormous in order to generate that kind of body. But I pulled up a paper from 2022 where Juno was studying Jupiter, and they're like, okay, so it appears to have a core that's about 63% of its diameter, and it's filled with like heavy stuff. But the heavy stuff is
63% the diameter of Jupiter?
Is the core, they think, and they think that there's like two layers, one that's metallic that's at the like core, and then one that's more rarefied and interspersed with like helium and hydrogen. And so they have this like double dynamo model for the magnetic field.
I haven't read enough of that to comment.
Yeah. And it seems like there's like you open this discussion by saying this, that astronomy is one of those disciplines,
Particularly planetary sciences,
because they're so hard to see, that we're limited by the observations that we can make, because science operates under the principle of observation, right? Like, I think that this is why biology on some level is a relatively easy field in which to make theories, because we have really good techniques for being able to observe things under a microscope. Most things that happen in biological systems can be transmuted towards optical frequencies. You can put it in a lab, you can mess with it, you can see what happens, and then come up with a theory. But with stuff like theoretical physics, where you have to build, billion-dollar colliders to see something, and even then it's very hard to see. Or like something like astrophysics, where you're looking out into the dark, cold reaches of space and hoping that you see this pinpoint that's happening.
Well, all you have is light, too, at the end of the day, which is really unique among the sciences. I always think about that. You can't put controlled experiments together in the same way that you can with test tubes. It's really, really unique.
And it's like, there's also the snapshot aspect of it, right? Because we're talking about processes that run on time courses that are far longer than a human lifespan. And so when we assemble the picture, we're having to assemble all of these frames that we weave together on the basis of they're likely to be related because
it's like you pull a book out that's had the binding ripped out, and you just have all these pages and you have to put them in order.
Yeah, well, yes, but you have actually like the entire Library of Alexandria, and all of the pages have been mixed. And so you're looking out and you're trying to assemble the books de novo, because what if it's not the same book? You know what I mean?
You're totally right. And I mean, I think to me that's why astronomy is fascinating, because you have everything at once, in a way. When I was in St. Andrews doing my degree, my undergrad degree, you could see that the astronomy cohort was reducing year after year, because the physicists among us, or the more pure physics people, didn't like the messiness of astronomy where everything had to be taken into account. But for me, that's where it was exciting, actually, because so much was going on. And I think you were also totally right in pointing that astronomy is quite special in that we don't control our experiment. The best that we can do is control our sample. And so we spend time thinking about, what type of stars, what type of planets we could be detecting, so that our sample makes sense. And then after, like you were saying, Anastasia, then you compare two samples together, you can make sense and say, oh yeah, we go from this to this. So because these are very massive stars and these are not very massive stars, then we expect that there would be an effect on planet formation scale, for instance. And then we can try to deduce it from that. But it's a lot of deduction. And in many ways, astronomers were the first data scientists, like when Netflix or Google, presents you with options without ever asking you what you wanted. They've deduced what you might want from, your past interaction, but also the interactions of other people, and seen a pattern that people who had liked, say, this film, or, had liked this image also had liked that one, and suspect that you would. And in many ways, they create as many, laws or patterns as they are individuals and can predict that way. Astronomy works in very much the same way. So we have to deduce. We can't know for certain what we have. We just have to be very careful and proceed progressively. And then once we have, we think that the theoretical framework works, we have to make predictions and then see where those predictions could be invalidated to verify that the theory is indeed sound or whether there is yet something else to happen. And to go back to the very beginning of the discussion, that's what happened with the solar system in many ways. We thought we had planet formation right because it seemed to work with the solar system, and indeed it does work very well with the solar system. Then looking at the rest of creation, you see that there were things that in a solar system didn't happen, but it's really interesting. Why didn't they? And it complements our knowledge of nature. And then there might be some things that might have happened in a solar system but we missed. So, for instance, a big scenario that explains why those gas giants, those hot Jupiters, are so close to the star is not because they formed near the star, but because they formed far, where ice was available, and had interactions between the planet and what was left of the disk brought the planet close to the star. And those interactions, we call that disk-driven migration, was actually a process that was invoked to understand the satellites of Jupiter and understand how the satellites in Saturn and around its rings were moving. And so this was a physics that was known. It just had not been appreciated that it would work on a planetary scale. And when people applied it to planets, it implied that all the planets would fall right away into the star. So it seemed like it was not applicable. It didn't make physical sense because Jupiter existed. So now, fast forward a few decades, we have plenty of planets that look like they have followed that process of disk-driven migration. So two things out of that. First, the planets don't fall into the star, so there must be a process to stop them or slow them down. So the process is not nearly as efficient as was originally calculated to be. But the second thing that you can ask is, why is Jupiter so far? It should have followed the same path. And then some people came up with a model called the Grand Tack model, and it makes sense now, where Jupiter comes in closer and closer to the sun. But it turns out that if you have a planet that is a bit less massive, it travels faster. And so Saturn came but caught back Jupiter. And when the two came to a very specific orbital configuration, that it inverted the direction of the forces between the disk and the planets, and the pair went back. And you can sort of see that there are evidence now, growing evidence, when you look at the solar system, that it has indeed happened. You see it in where the asteroids are, what mixture of materials you have. You can see it in the small size and small mass of Mars, which otherwise, at the distance at which it is, should have been a planet just like the Earth. And the fact that it's so small, a tenth of the mass of the Earth.
Can you break down that mechanism by which that inversion happens? You glossed over that, and I was having a hard time picturing it. Like, what is the tipping point that causes the change in the motion of this?
It's the fact that Saturn caught back with Jupiter. So what happens is that as the planet migration scenario would have it, the planet carves a gap into the disk. And on either side of that gap, there's a sort of pileup of material just before and just after the planet. And those act on the planet and create a force. And typically, the force goes outwards for the gas. And so it means that the planet needs to move in to respect angular momentum. So the planet moves in. The problem with Saturn is that as Saturn comes in, it has its own set of bumps on either side. But because it's a smaller planet, it's smaller bumps on either side than for Jupiter. That's important because as the two planets come together, they enter the same gap. And so you end up with a big bump in front of Jupiter, a small bump outside of Saturn, but no bumps in the center. And so it means that then the gas moves backwards. It moves forward inwards, and the planets move backwards and go back. That's
they're sort of pushed out of the way as the gas fills in the gaps, something like that.
Yeah, it's just that the presence of Saturn in that gap inverses the balance of the forces, and then everything goes back. And it's a very clever idea, and I think there is enough evidence that it might have happened in a solar system. And so in many ways, thanks to exoplanets, we now learn a little better about our own planetary system. And so we've understood something about physics that we thought wasn't needed. And in many ways isn't that needed to understand Jupiter and Saturn, but in the end, to understand the whole picture of why Mars is that way and why the asteroids are that way, then you need that process, and that process
Now,
is the same that
now do you see
worked.
that disk still remaining in these hot Jupiter situations?
No, the disks dissipate very rapidly. They dissipate in about 10 million years at best. So
So in
when
those cases, you don't expect those Jupiters to wander back outwards.
no, you don't. No.
And what's their fate ultimately? Will they be cooked down to a core? Will they end up looking like a rocky planet, or what happens?
It's also a good question. So there are some people who think that. I think most of them will be fine until the star starts evolving and becomes bigger. So every star evolves, like our sun will do the same. And then it grows bigger, so the sun will become almost the size of the orbit of the Earth at some point. And so those hot Jupiters will be engulfed at some point, like any planet, close in enough or too close to the star.
When we're looking for exoplanets, I remember I can't. I'm trying to pull this up and I can't pull this up right now. But I came across a map of where they were located inside the Milky Way, and it seems
Mhm.
like there was kind of an arc by which we were looking, and it seemed like it was backlit maybe by the greater mass at the center of the Milky Way, and so we had this kind of selection bias towards looking for planets in one direction. Is that accurate?
Mm, yes and no. It's not that we were biased by where. It's more that there was a more powerful telescope that was looking in one region. So ultimately, to find an exoplanet, what is important is the brightness of the star and then how good your telescope is. Usually, a larger telescope, so a larger mirror on your telescope, will mean that you can accumulate data faster, but also that you can separate the number of stars, and also the area on the sky that you look at is going to be more restrained, smaller. And so for a long time, telescopes that were operating from the ground were 10 centimeters in diameter. They were pretty much zoom lenses, actually. And so one of the experiments I used during my thesis was just that. Canon zoom lenses put on a telescope mount
Oh,
and
wow.
operating with a scientific detector. And so we could observe a lot of bright stars over a very wide area of the sky. When NASA launched the Kepler spacecraft, what they chose was a telescope that was 10 times bigger, so a meter in diameter, and decided then that they needed a certain number of stars within the field in order to have a certain probability of detecting a number of planets that they had as part of their objective. And because of that, then they were observing in one small area and were observing stars that were quite far away in order to have enough stars within that area. And that's what leads to those patterns. But in many ways, most people in my field don't think it matters too much to look in various directions because the stars in our Milky Way kind of mix anyway. So, like our sun was probably born much closer to the galactic center than it is now. So it has moved. All the while, it has been totally fine for life on Earth, and it's not very different from any other stars. And you see young stars nearby us and very old stars nearby us. And so there's a mixture, a bit of everything. But there could be some populations that are a bit different. So there might be a certain bias indeed in certain directions. Or if a Milky Way was built progressively, so if for whatever reason in that direction we were sensitive to stars that came with a slightly different chemical environment when they were born, then we might have biased our results a little. But by and large, I think most people don't think that's the case. Yeah.
Fair enough. Do you have something?
I was going to change back a little bit, but go ahead.
I think I was going to change too. Go for it.
All right. Well, I just wanted to. We were talking about these different formation mechanisms, and with regard to the core accretion, do you sense that people are studying the role of chemistry and electrostatics
That's
in
exactly what I was going to ask.
that dust moment when you go from dust to something that actually has gravitational heft?
I'm not a theorist, so I don't know too much. I know that electrostatic forces are important when you have very small particles. So we call them van der Waals forces, for instance. So at that moment, it's very important. Static is important, and there is a certain, things tend to stick a little together. But it tends to be limited for very small sized particle. When you enter a larger particle, then like the size of pebbles, for instance. I don't know if you've tried to charge a pebble or make them stick together. They don't tend to do that.
Yeah, I was thinking of the very early moments, and
Yeah.
particularly reactions like condensation reactions, which are natural, like cooling reactions. I wonder if anybody's thinking about those sorts of things.
So one of the first researchers I worked with was thinking of planet formation like the creation of a cloud, in a way, like nucleation. So when a cloud forms, then you need to have at some point going from gas to droplet, and was thinking about how to apply those physical principles to planet formation to various degrees of success. So I don't think that's that's not certainly the credo at the moment. It's not. It doesn't seem to
Not a
work too
popular
well.
idea yet.
Not very popular, but if we still can't, so there is still something. There's a big problem in planet formation at the moment, because when you look, so I participated, for instance, in a discovery of a system called TRAPPIST-1. It's a tiny star. It's about 10% of the mass of the sun, and around it, it has 7 planets, more or less the mass of the Earth. And when you compute the mass of material that was in a disk before, so typically a star has a disk which is about, between 5 and 10% of its mass around it. And there is a certain fraction of the disk that will be made of material, of metals, and the rest will be hydrogen and helium. And when you compute those, you realize that nearly 100% of the dust in the disk transformed into planet. And even if you get, like the story a little wrong, it's a massive, it's a really efficient process. It means that it must be evident. They cannot not be a planet, effectively. And it's strange, we're all in awe in front of, say, nuclear fusion. Nuclear fusion is a very inefficient process. What powers stars and all the light that we see in the universe, pretty much, is a process that transforms 0.007%, if I recall well, of the hydrogen into helium. It's tiny. It's really inefficient. And so we have a process that, like the number of exoplanets, the configuration, screams to us that planet formation is a dead easy process. It's an inevitability. And yet it's difficult to do. And so we have a problem. And I've shared that with some friends, and they agree. And we're puzzled, but eventually we'll get it. It has to happen. It must be something to find. And so that's what I was telling you earlier. There must be some physical laws that underpin this, because it's too good to be true. It's not random. It has to happen. And
why do you think they're starting with so much dust? Is that just because of the very young systems that you see?
They actually don't start with that much dust. Ultimately, they start with about 10 to the minus 4 in mass compared to the star. It's really, really little. And it's what there is out there. It's not very different from, say, you take a gas cloud to the content of dust that there is in there. When we were talking about the difference between stellar and planet formation, so the star starts by forming because the gas cloud collapses. When you have your protoplanetary disk, so you have a disk of dust and gas, what happens is that the dust tends to settle towards the center and then accumulate and agglomerate. And so it starts from the dust itself, and that's why it's gas poor. The gas doesn't have, it goes too fast, it's too hot to stick to those dust particles. And at some point, most of the gas disk gets evaporated by the star, and so it leaves objects that are mostly dust rich. But it's not because there is particularly more dust into the disk as there is in the star. In fact, there is just as much dust in the star as there is in the disk. There is at least as much mass. So if you count all the mass of the planets, the hard part of the planets, there must be as much of this in the sun, because it all came from the same place.
And does
more
that
or
appear
less.
to be the case in something like our solar system, or
Yeah, I think so. As far as I know, yes. I haven't checked specifically, but yeah, I think that's yeah.
and so
Certainly it's accepted. That's seemed to be the one thing. And I remember some people trying to find metal poor stars, so stars that have a lack in what we call refractory elements, so silicates, carbon, any of these kind of things, because there would have been so many planets forming that they would have prevented that stuff from falling into the star. But as far as I know, there hasn't been any difference. And even if the planets were to increase a bit in mass and capture a little more, they wouldn't have captured that much more to make an effect on the star. So it seems to be pretty balanced, as far as I understand.
And so where does if the gas gets dissipated before okay. Does the gas get dissipated before planetary formation is finished?
All the while it happens. So it's a game of it's a clocking. It's a time game. So planets need to form quickly before the disk dissipates. Dust remains. The remnants of dust are still in the solar system, asteroids, or the rest of what happened of planet formation, but you don't see any of the gas anymore. We know the planets formed very rapidly, so probably Saturn, we have an age, I think, for the formation of Saturn that is pretty quick, between 3 and 5 million years after the birth of the solar system. And we know that because of the position of because of the properties of one satellite, which is really weird looking. And from that, it could only ever happen at a specific time in its formation. And it has to do with radioactivity and all that. But it means that satellite must have formed between 3 and 5 million years. But if the satellite was there, Saturn must have been there already. And so we know that Saturn must have formed at least in less than that time. So you can see it just about works. Like Saturn can form in about 3 to 5 million years. Most disks have completely dissipated by 10 million years. And actually, usually by 5 million years, most of them or half of them are already gas-free in a way. There's only dust left.
And that whole
And then,
grand tack business happened in the course of just a few million years like that.
also, yes. And so all of that needs to happen very, very rapidly. Yeah.
So one thing that I've seen photographs of is these gas disks around young suns that have very clear tracks in them that have been, eaten away by the planets that are rotating. And something that I think about is that we have like a heliospheric current sheath, right? And it's this like weird kind of folded up structure as it's represented. Is this accurate?
So you mean the heliosphere, like the area around the sun protected by a magnetic field, or
Yeah, but
the
there's
suns?
also this thing that's is it the current sheath?
Well, I guess it's just that the stellar wind is preferentially emitted at the equators, and it forms this kind of ballerina skirt that then folds
Right.
back
Yes,
on
I
itself.
sort of see what you mean. Yes. Okay.
Okay, so we have right. So it's basically this. It looks like Shiloh said, like the ballerina skirt that's like twirling around the sun, and it has like depressions and maxima. And that to me looks like something that is a dynamic structure that emerges with time and stability and increased rotation. And I've wondered, is it possible that there's some kind of motion that's happening inside of early stars that's creating these concentric rings of concentrated gas the way that you would on like a Chladni plate? So
I
have you
don't know
seen the
what
videos like
plates
with a
you mean.
Chladni plate is like you take a plate, you attach it to a speaker, you put sand on it, and then you
Right.
vibrate the speaker, and then it creates these shapes. And I'm like, is it possible for the observations that we're seeing being not that the planets are moving in the dark spaces, but that the planets are actually concentrated in these rings of dust, where the planets are that the dust is already kind of concentrated for them and constrained, and so they form within
By
those
sound
rings.
waves, you mean?
Maybe not necessarily sound waves, but there's a lot of different cycling systems, right? I mean, maybe acoustically, but you also mean more just like the electromagnetic cycling of the sun?
Yeah, because it sounds like we're saying that like the dust phase is electromagnetically sensitive. And if there's a process in the young sun, which is some kind of like electromagnetic pulsation, is it possible that that could be creating the structures that we see?
I mean, I sort of see where you're going. To some extent, I would say yes. So, for instance, we know that so every object vibrates. And like you say, this sort of vibration, you sort of see the inner vibration of Saturn in some of its rings. So, if you want actually an interesting topic, there is something like this chronoseismology or something like that. I think that's the word, where you can see a pattern in the ring which is due to some object probably far in the deep interior of Saturn. And as Saturn rotates, it creates a sort of beating pattern as seen from the orbits, because you see an object that sort of rotates. And so it looks like it's doing something a bit like that. But it's very, very minute. Now, we know that the magnetosphere of the sun must have affected the inner part of the protoplanetary disk. It must have truncated the disk, and we see that on other stars as well. So we see a cavity. We also know that the disk itself has its own magnetic field with its own lines, which is launching a wind, and that to some extent, some ionized particles and dust would be affected by that and be evaporated. Now, whether you can concentrate using that, I don't know. And I don't know whether anyone has done this. And I don't think the pulsation of the star would be enough to do it. But yeah, I can't comment much more. I don't know much about the heliosphere also, but it does look static, but I have a feeling that it's very dynamic and depends very much on where the sun is and how, where the sun was in its time. I'm sure it was very different when the sun was young and a lot more powerful. At the beginning, the sun probably had jets also, in the first few million years. So, those processes no longer happen and were actually at the time quite destructive. And the reason actually why the sun has lost its angular momentum, like why it runs very slow instead of fast. Yeah, but it's an interesting idea. Sound, I don't know, to some extent, because some sound does happen, and so for this to happen, you need a resonant chamber. Yeah, that's like I think what the problem will be. It's similar to having a microwave or to having a musical instrument. You need something that resonates, and whether a disk could work like a cavity, I don't know, like something that would be bound enough to make waves resonate. I don't know if it's strong enough for that. Maybe vertically, but azimuthally, I don't know. I don't. It's an interesting idea. Like maybe I'll quiz somebody at some point about that.
That'd be cool. I'd like to know.
Now, I do have one more question about something you mentioned, but I do want to talk about these two papers before we finish. Do you think that we could take a short bathroom break before we get into those?
Yeah, I would need one too.
Pardon the interruption, but before you go, I just wanted to take a moment to remind you to purchase tickets for our very first scientific conference, Demysticon 2024. It's going to be held in Austin, Texas on April 7th and 8th to coincide with the total solar eclipse that is passing through there. We have about 1 minute and 30 seconds of totality for us on Monday, and the rest of the time we're going to spend exploring ideas as a community, and we really hope to see you in Austin because I think it's going to be a really special event. For now, back to the conversation.
You mentioned this 1% chance we could lose a Venus-like planet, and the flip side of that is perhaps even more hard to imagine, but what happens to those ejected planets? What is I assume it's extremely rare, but what are the odds that that planet could end up as an adopted orphan in another solar system?
Yeah, it's a good question. So at the moment, there is growing evidence that there are a large number of these rogue planets. It's actually affecting our very definition of planet, because at the moment, the definition of planet is a world that orbits a star, something round that orbits a star. So obviously, if you lose your star, do you cease to be a planet? I don't think that's true, but it becomes harder to define, I guess. And yeah, so there's a growing body of these kind of ejected planets, and the key question was whether they were born in isolation, a bit like the objects that we talked about that Anastasia brought up that were found in Orion, or were these ejected planets, or is it a mixture of both? And also, I think a key question at the moment is really how many of them are there, and what is the sort of power, the sort of mass distribution that these planets have. Does it look like the observed exoplanet population, or is it a specific class of planet, etc., etc.? Now, whether those planets end up in other planetary systems and adopted, so I think, there is a chance that you would have encounters in a system, like for instance, there are stars that are flying by the solar system every once in a while. I think there was one, I don't know, 30,000 or 300,000 years ago. I don't know. Like some friend showed there was a star that came quite closer than the nearest star is to us, for instance, a little while ago.
Was that Sean Raymond?
That wasn't well. So Sean Raymond, I don't know if you talked to him, but you should talk to him. Yeah,
Yeah, cool. We had him maybe last month.
Yeah.
This was something that I guess the reason that I ask you this is because when we asked Sean about this, they didn't have the data of these co-rotating Jupiters, and the idea that something would already have that angular momentum, I was thinking might lend it more to capture than something that was just whizzing past on its own. And so
the problem is it's very difficult to stop something into a system because there's no braking mechanism. So most things that are falling towards the sun, what they do is that they pick up velocity as they get closer and closer to the sun, and then they go so fast, and then they go about the sun and then go as fast out as they came in. So capturing something in the solar system requires another dynamical interaction somewhere. So you need to have another planet. So you need to probably go already within the plane of the solar system, so you have more chance of encountering another planet. And really, the only planet that you want to care about is Jupiter. So it needs to be very, very, focused. And you can't get too close to Jupiter nor too far away. And then you affect Jupiter to stop, because all that angular momentum that you have as an incoming planet, you need to give it somehow. You can't get rid of it. And so I don't know how that, it seems difficult. You don't have gas to stop you. So while you have a gas disk, you might, but without anything else, I think it'd be very difficult to capture.
You mentioned earlier when we were talking about the pebble formation process, where you have the draft pebble and then you have the other ones that kind of accumulate behind it. Is that not a plausible mechanism as well, where something comes up behind the solar system that's moving objectively fast, but relatively slow relative to the solar system or any other star system?
Yeah, if it were exactly like very, very slowly, then yes, I think you would have to have very small relative velocity for capture to happen. Yeah, otherwise, you have too much angular momentum anyway, and you have to shed it. While you can't shed it, that's a problem. Now, we know that there are objects that are going through the solar system. So we've had 2 asteroids that came from other stars that went through, Oumuamua and Comet Borisov, I think. So we know that these objects do go about, but those were asteroids, they were not planets. Now, I think if you imagine that most stars have planets, most of them will eject 1 or 2 planets during their lifetime, maybe 3. Then there must be more planets out there than stars. And so there should be more encounters with these rogue planets than with stars in some way.
You mentioned that they would be expected to be in the same ecliptic plane if they were going to be captured. But I saw some papers. I saw a paper you wrote, I don't know how long ago, or at least you were an author on, I believe, that was regarding these, was it a hot Jupiter, some sort of exoplanetary, pretty large exoplanet that was perhaps at a pretty serious incline to its ecliptic. Do you know what I'm talking about?
Yeah, so one of my earlier pieces of work were to measure the angle of the orbit of the planet compared to the angle of the equator of the star. And there is a large fraction of the hot Jupiters that have these inclined planes, which is telling us something about the way they migrated without the disk in that case. But I don't think that they were captured, because they were, again, they're on circular orbit. And I mean, if you were to come in at any random angle, if you get really close to the star, what will happen is that tides will deform your planet. And that is good to actually transform some of the energy that you have, because then you dissipate it as heat, but also to transfer angular momentum between your object and the star, your planet and the star. The thing is that you have only one chance to do that, and that's what makes it particularly difficult. It is if you had a really eccentric planet already, to actually make that orbit very eccentric to very circular takes already something like, I don't know, 1 billion years or something like that. So imagine the number of orbits that you have. You have at least, 1 billion orbits, in there. And probably way more. So you've had many, many, many interactions. And already for this kind of planet, you're at extremes where the planet is in danger of being destroyed because of the internal forces that are applied to the planet. It might actually get too hot and just dissipate. That I don't know how you would be able to capture something just like that.
I guess that's why I was bringing up do the binary pairs of Jupiters change that balance at all? Like if they already have a circular orbit established with themselves, does that change any? This is maybe a question for Sean Raymond instead, honestly.
Yeah, I think you should ask a dynamicist, although beware of dynamicists. I've been told by a friend they can explain everything. They always have a good solution to anything at all. But whether
that's a good friend to have in your
another...
back pocket.
Yeah, exactly. I think from what I understand with those binary Jupiter objects is that they're quite far apart from one another.
Right.
Now, if you do have a binary star, I still think that you have this problem of where to put your angular momentum. It still is a problem because you come in with quite a lot. So, yeah, I think capturing is always difficult. It's very difficult unless you have a medium, or likewise, Anastasia saying, you are moving with relative velocity. So, for instance, in a birth cluster, in a cluster in Orion, we have many stars that are being born, and planet might be ejected from these systems and things like this. All of that group of stars is sort of following more or less the same trajectory at the moment through the galaxy. And so that's the good time to be captured by something else, because at that moment, so long as you move relative to something else, at the moment where you leave the rest of the group, then the two objects are quite close, then naturally gravity, eventually will make them rotate around one another. But you're captured at really, really long distances, not, like suddenly another planet comes and takes Venus's position, that seems to me really, really unlikely.
Sure.
Yeah, so maybe that's a good segue into talking about binaries and this very bizarre system that you found, this tattooing-like system for the Star Wars aficionados out there.
Mm-hmm.
Was that extremely shocking? Was it predicted, or?
Well, let's say what it is first.
Yeah, fair enough.
Yeah, let's describe a little bit. So yes, the paper I sent you was a discovery made by my team that I was very happy about. We discovered the second planet in a system that was known to already have one, and both of these planets orbit two stars at once. So we have two stars that orbit one another, and then the planets orbit around both at once. They don't orbit in between. They don't orbit one and then the other. They just both at once. And for that, Tatooine is the most famous example. In the preamble, and generally speaking, we were wondering, what people had imagined before. We knew of exoplanet when we only knew about the solar system. So actually, the oldest depiction of a second binary planet is from a book that was published in France in 1937, where you have an image of a planet which has shadows of two colors, because they're stars of two colors that are casting shadows. So even before, before we knew of exoplanets, and people had wondered whether this kind of configurations had happened, if only for the mental stimulation of thinking about it and what it could look like. Then I think there's a long period of time when people were wondering whether they existed, and there are plenty of reasons for planet formation where it's difficult to imagine those planets, because imagine when you have a star or a single star, you put your own fist into a bucket of water, you turn your fist. Mostly the water will remain fairly stable. There would be a few ripples, but not much. put two fists in a bucket of water and start turning the two fists around one another, waves will develop. And those waves actually prevent the accumulation of dust into planets. Because what happens is that instead of everything going in the same direction, suddenly things have crossing orbits. And it means that, a bit similar to the discussion we were having, when you have relative velocities that are very small, you can catch another object and then stick to it. But when you encounter it, then you have destructive collisions. And so it makes planets very difficult to form right next to the binary. Far away from the binary, it doesn't matter too much. And so the same planet formation process can happen really far away. And so the way we think those planets are formed is that they formed more or less where Jupiter and Saturn are found nowadays. There, the effect of the binary was almost nothing. And imagine if you were to put your two fists into a lake, likely on the other side of the lake, no one will notice that you're messing with the water, right? And then the planet used disk-driven migration that we talked about in the context of the hot Jupiters, notably, to come closer. And that's why we're finding them. But originally, there had been a sort of, because this is hard to form, those planets, people had already wondered whether those planets, could even exist, even though science fiction had imagined them. And then some people started looking for them, and then they found nothing. And they tried for a while. It's not by lack of trying. They tried for a while, but the methods were really difficult because when you have two stars rather than one, it actually creates a sort of interference in your data. And it hides the presence of planets, so it makes it harder. So it was a Polish team, actually, that started this work in about the year 2000 or something like that, maybe a little earlier. And in about 2010, they published the results and said, well, you know what, we don't know if they exist, but we can't find them. And we can't find them maybe because they don't exist, but possibly also because our methods are not just, good enough to find them. And so it was a bit of okay, well, darn. But then a year later, the Kepler telescope, so NASA's mission that we already alluded to, that was looking, quite far into galaxy, was observing many stars randomly, including pairs of stars that happen to eclipsing binary stars. And very rapidly after the mission was launched, they found that there was on that signal, so you see the light, in a telescope, you never see, the stars individually or the planets or whatever. You see the combined light of all the system. And so the two stars orbit one another, they pass in front of each other, create an eclipse. So it means that the light is varying. At some point, it drops when the two stars are in front of one another. And that is a very regular pattern. But then on top of that regular pattern, there was suddenly a little blip. And then there was another blip. And then there was another blip. And in between these blips, those were caused by the planet passing in front of one of the two stars. And compared to a regular planet, which when it passes in front of the star, it pretty much comes back all the time at the same, like every orbit is regular, the planet comes back. There, the distance, the time between those blips of the planet, those we call transits, was unequal. And it's unequal because the source of light was moving. So sometimes it passed here, and sometimes it passed there. And there was a telltale sign. There's nothing else that we can think of that could produce this signal, if not what we call a circumbinary planet, so a planet that is around both stars. And that was an American team led from San Diego, I believe, roughly, that found that. And rapidly they identified about 10 other systems like that. And so there was this disconnect where on one hand, people had thought they were not really possible, and people had tried to find them and didn't. And on the other, they seemed to be actually pretty abundant because with that other method that was just casting a very wide net, they found actually quite a lot. So I was really surprised by that. When I saw the first one, I said, well, there must have been one somewhere in the universe. So cool, really cool observation. I wish I'd done that, but okay, cool. Somebody else did it. Now we know it exists. But then they found the second and the third and the fourth and the fifth. And then I started questioning myself. I said, well, if there are that many, surely we must be able to find them with the method that the Polish people had initially decided, which is cheaper, using ground-based telescope, and usually less biased as well, in terms of, the sort of the way we look at the system. And so I started a project to find them. And then this paper was actually the first true discovery that we made. So we confirmed other planetary systems And it was the first one that we discovered that no one had known before. And so it opens the door to finding many more, actually. Now, why are we finding these planets? And why are we interested in them? It's not just because they're exotic and fun to observe. It's also because it's telling us something about planet formation. So what's interesting is, again, that wave pattern when the two stars are orbiting one another. That wave pattern prevents planet formation within a certain area around the two stars. So that depends only at the separation between the two stars, which is a function, because of Kepler's law, of the orbital period. So if you have a binary that has a 10-day period or a binary that has a 100-day period, then the region where planet formation is impossible or thought not to happen is much larger around the binary that has a 100-day period, because that one is much farther away. So there's a larger area over which there are waves. And what's interesting is that because that area of impossible planet formation is larger, it means that you can go beyond the ice line, the water ice line, or beyond the CO2 ice line, or beyond the CO ice line. And so you can test whether planet formation can still happen at each of these places where you expect more planet to be formed, because instead of having just rocks, you have rocks and ice. And so it allows you to test a core assumption, effectively, of core accretion theory, that you need to have ice in order to build a core for a planet. And the idea is that around the wider binaries, we should not expect gas giants, because then we reach too far into the system. We reach into areas that have had, plenty of ice, I guess. So you would expect planets that are more enriched in, say, all of those ices, and their atmosphere to be poor, respectively, in those, because they're stocked in a way in a core. And thus test some of these elements. And that's what I was telling you earlier. We have to devise a good theory and then find out what it implies in another setting. And while I think most physicists or biologists would create an experiment and try fiddling with it and controlling it, in astronomy, you find another setup, another environment. And you say, in this environment, if the same physics holds, then this changes. And if this changes, and then it should produce that. Now, do we observe that or not? And if we don't, then we must change the theory or revise it.
How difficult is it to deconvolve orbital distance versus orbital speed? Because if you have something that's really close in going really slow, could it look like something that's really far out going really fast?
Kepler's law prevents that. So the speed of your orbit is entirely dependent on your distance and on the orbital period. The closer you're in, the faster you go. You can't go slow. If you were going slow, you'd fall into the star.
I see.
So you would not be there anymore.
Man, I'm really struck by how important the circumstellar medium is in all of these formation paradigms. Like, we're talking about fluid dynamics and these wave phenomena and so forth. And it's just amazing to me, because when you think about gas, you think about, a balloon or something that's like you think about this rarefied substance, and you think, like, how can that possibly have any effect on these huge bodies? And yet it seems to. Can you help me make sense to myself about that a little bit better? Because, we're talking about these force, like pressures, like viscosity and these slipstreams and everything, and it's mind-boggling.
It seems like it's a kind of a contained system, though, at least partially, right? It seems like it's captured to some degree and is bound together. And so,
it's still these tiny little interactions, there's rarefied. I mean, maybe it's just a matter of time. Help me out.
I think it's mainly because of the mass, the sheer mass of it. The gas disk is way more massive than all of the planets combined. So it has more of an effect until the planets dominate. So you have to think, at the beginning of the disk is about 1% of the mass of the star. Jupiter is 1,000th of the mass of the star. So the disk is 100 times more massive than Jupiter. So
in what kind of volume?
Yeah, in a large volume, but that's the dominant. Gravity is very strong. So that's. I think it dominates because of that. And when you start, so actually, when we talked about this disk-driven migration with the planet carving a gap, which is similar actually to what you were talking about, Anastasia, with the rings that we see in forming systems. When you create that gap, actually, that's when the planet starts dominating the local mass of the disk. And so actually the planet moves at the velocity that the gas moves at, more or less. But before it does that, the gas completely dominates the planet and brings it more or less where it wants. So yeah, it's just because of sheer mass. It's the mass that does. It's not when you're talking about particles, it's the headwind, like we talked about. When you're talking about small planets, the headwind can have an effect, but not huge. Then the interactions with the gas, so building a wake, like we talked about, sort of overdensity before and behind the planet. This is a wake. Think of it like when you're surfing, for instance, you create, a wave on either side. It's as if that wave is, as massive as your planet, and so it will have an effect on you because the disk has an effect on that wake, and because you're trying to maintain that wake, then it has an effect on you. It's odd to think, I agree, but yeah, it does. So it's like, think about, no, I don't think that's quite a good analogy. Yeah, let's leave it like that. I think it's just because of the mass.
I mean, the mass, but also if we have the gas and the dust is ionized.
I don't know enough of that. Probably not too much. Some of it will be. So some small particles will be and will follow magnetic field lines. But when you have a planet, it's no longer, charged. A planet is not really charged.
Sure. So I guess I'm thinking of what kind of force could create a disk that hangs together like that moves as one. And so it's like if the dust in the disk is
its initial velocity, angular momentum. So like it's the same way that you make a pizza. When you have dough and you make a pizza, like you rotate it and then it extends naturally. And what keeps it from going up is velocity. So it goes along one axis. And what keeps it from going too long is a certain resistance, like the flexibility of the dough. In our case, that's gravity. The star is still trying to keep everything together. But that's just velocity. It's the same if you do pottery. Try pottery. You start spinning your wheel. Immediately, things are going to flatten very, very rapidly.
Definitely.
Okay, so now you're looking for water on other worlds, and you found some sort of interesting correlation corresponding to, I believe it was the carbon dioxide levels. Can you unpack that for us?
Yeah, so it's a very recent paper for that, and I would say so. The gist of the paper is that, well, maybe a bit of context before. So in exoplanets, or like in astronomy rather, we have a concept called the habitable zone. And the habitable zone, otherwise known as the Goldilocks zone, is the not too hot, not too cold sort of zone. And if you have a planet, so a habitable planet in our jargon is not a planet where you can go immediately land there and go camping. It's a planet where if you had similar conditions to the Earth, atmospheric and geologic conditions, then water would be liquid on the surface for billions of years. And that's a key element for us to prioritize which planet to search for life on, because we're looking for biology in a cosmos. So we're trying to find out whether the planets that we detect could have biology. Then looking at planets that are too hot would be a bit of a waste of time, and planets that are too cold would be, so to speak, a bit of a waste of time if we are interested in biology. I actually don't share that thought. I think that we need, in order to understand the biology, the planets that will have biology, we need also to understand the limits, how hot and how cold, and therefore to go observe for those. But nonetheless, the concept exists of habitability. And so habitability has always been defined as the ability to preserve water in a liquid phase. And compared to that, so the issue is that it's a purely theoretical concept. So when we find a planet, we can measure how far it is from the star, and we know how hot the star is, so we can figure out roughly what temperature the planet is going to be. And that defines the habitable zone. So if the planet has the right temperature, it's habitable zone planet. But ultimately, we don't know. And for instance, the temperature on Earth is dominated, or is influenced, not dominated, by our atmosphere. And our atmosphere is warming the planet. So if you remove the atmosphere of the Earth, the planet is a lot colder, we have a little bit of greenhouse effect, which warms us to balmy 13 degrees centigrade, and we're all happy for it. And it has remained so for billions of years. So where we started with the paper is that there's a concept in astronomy, another concept called a biosignature, where if we look at the spectrum of a planet, we can extract and figure out that there is life there. So it would be, say, a gas that is emitted only by biology. And so we have that very well defined, but we didn't have a habitability signature, a way to empirically determine that the planet has indeed liquid water. And so with my colleagues, what we defined was, first, we need to actually define that word, a habitability signature. So in the paper, we coin it as hab signature. I think it's a terrible word, but we couldn't think of anything better at the moment. But whatever. It allows us to speak of something we can observe that tells us the planet actually is habitable, meaning it has liquid water. And then there is the other thing about, then after defining that, what is a habitable signature? And there's a well-known process, so we didn't invent anything with that. We just borrowed. And it's a process that is very well known in geophysics, but not so well known in astronomy, that there is as much carbon dioxide in the crust of the Earth in the form of limestones and other rock formations than there is in the atmosphere of Venus. So the core idea is that both planets were born with a lot of CO2. What happened to the Earth is that the CO2 has been sequestered by two processes, mainly by geology, by being dissolved into water, and in a lesser extent by biology. And we know about it, right? Because we're trying to now sequester carbon using trees and other methods. And if you look at Mars, again, you look at this atmosphere, it's mostly carbon dioxide. Venus is mostly carbon dioxide. And so we're there, well, maybe the lack of CO2, if you have other planets with plenty of CO2 in the system, must tell you that the CO2 must have gone somewhere. And the only process that we know so far is dissolution in water. So there's, at the moment, our atmosphere is 1 bar. If we were to remove the CO2 that is dissolved currently in the waters of the ocean on Earth, our atmosphere would add 2 bars of pure CO2 on the Earth. So there's twice as much atmosphere locked into the ocean as there is in our own atmosphere. This is to show how much of it there is. And there is, probably, 40 or 50 atmospheres worth in the rocks. So it has been a very efficient process across eons to sequester that. And we're the beneficiaries of it nowadays. And so our premise is that let's look at planets. So going back to TRAPPIST-1, for instance. So that system is the most optimal to study the atmospheres of rocky planets. And at the moment, the most propitious as well to detect biology elsewhere. And that's just because of the properties of the stars and the planets around them. They just give us a lot of signal. So the thing that we have now, so we have a lot of hope about TRAPPIST-1 because it has 7 planets, so it means that we can start studying the diversity of atmospheres. If you look at the solar system, we have Venus, Earth, and Titan as a satellite of Saturn as the 3 types of atmosphere that we know. And we have 7 planets. So maybe we will get 7 different kinds of atmospheres. We don't know what we're going to find. So it's very exciting. So the first thing that we want to know is whether the TRAPPIST-1 planets have an atmosphere. And it turns out that CO2 is the easiest molecule to detect. And that's because even if you have very little CO2, it's very opaque. And so you see it very well from afar. And this opacity is actually the cause for climate change. That's why CO2 is so efficient at trapping heat, because it's opaque. It creates a wall, effectively, or blanket, as we called it, around the Earth. So what we propose is that instead of going, in every direction and try to find these atmospheres and study the TRAPPIST-1 planets a bit however we want, maybe let's focus on the CO2 specifically, because the CO2 in very few observations will tell us whether there is an atmosphere. If none of the planets have an atmosphere, we can stop there, because even if they have life below the crust, we won't find it. Forget it. We have trouble on Mars already. We won't do it on an exoplanet. However, if it has an atmosphere, it means there is a reservoir for then biosignatures to be found. So then the next thing that we say is that then intensify the observation and measure how much CO2 there is. And if you see that there is very little CO2, then chances there's an ocean on that planet, which makes it a really, really favorable planet to search for evidence of life. And it so turns out that right next to the CO2 feature in our instruments, there is an ozone feature. So if there is a lot of oxygen on the planet, it would be difficult to find the oxygen. But oxygen under UV radiation transform into ozone. And so if we find a little bit of ozone, it means there must be a lot of oxygen. And so it means that in one observation, we can actually not only find that the planet is habitable, but also whether it is inhabited. And so it gives us a path, effectively, or a protocol to follow to hopefully maybe find the first evidence of biology elsewhere and do it in a workable way within the lifetime of the Space Telescope James Webb, which is limited and is currently the only one that can do this kind of measurements. And so it's why it's an important paper, because it's, or why I'm I don't know, so enthused about it, is because it's, for a while we weren't sure that the James Webb Space Telescope would be able to find evidence of biology elsewhere. But if we follow as a community this sort of approach, then I think we have a shot. So if there is life like there is on Earth, on TRAPPIST-1e or F, one of the two of the planets in the system, then we have a good shot at finding it by focusing on CO2.
That's very cool.
Do you have a sense of why Venus doesn't have an ocean, or planets that, have these heavy CO2 atmospheres? Why didn't they obtain water through the same processes that Earth did?
It's a very good question. So the leading thought at the moment is that Venus used to have water, but lost it. So, and it lost it because it became too hot. So that's one of the extreme risk of climate change, is that you enter what we call a runaway greenhouse effect, where the planet gets too hot and more water vapor enters the atmosphere. That increases the greenhouse effect. So then it's hotter. So then even more water vapor goes into the atmosphere. And then if the water goes into the stratosphere, it becomes affected by UV radiation. UV radiation separates hydrogen from oxygen. Hydrogen escapes, and you've lost your water. And that's what we think happened on Venus. Now, some people differ on whether that ocean was very early on or whether there was one recently. And some papers suggest that there was an ocean as early as about 1 billion years ago, so fairly recent. Others suggest that the planet has been dry for a very long time. So I remain fairly agnostic on that topic. I'm not an expert on Venus, and I don't really understand all of their arguments. But some planets might have been born with an ocean. And there is the same debate about Mars. We know the northern plains of Mars look like they have less craters, which implies erosion, and water is by far one of the most efficient eroders around. So it looks like the planets were born with some water. It's just not all of them keep it.
So in the case of Venus, was it, it seems like there's two possibilities. One, that all that CO2 was originally dissolved, and one was that the ocean was so short-lived that it didn't have time to dissolve it. And if it was dissolved at one point, why didn't the atmosphere lose the CO2 at the same rate it lost the water? Is it because the CO2 doesn't break down the same way?
So the CO2, so I think the bigger issue, I think, so if the water is transformed into vapor, then it would release the CO2 in the atmosphere eventually. Now, I'm not an atmospheric chemist, so I don't know what would happen to the CO2, but because it's a heavier molecule, I guess it would have a harder time going up, and it wouldn't be necessarily as easily destroyed by UV radiation as water is. I think a greater issue is if there was a large ocean on Venus and it was as efficient as on Earth to sequester the carbon into the crust, how was so much CO2 released afterwards? And I don't think we looked too much into that. I mean, my suspicion is that there wasn't necessarily much of an ocean to begin with, although some of my co-authors seem to think so. Another option to do it is that we know that there was or we suspect there has been a large volcanic period in Venus, which might have actually released much of that CO2. But again, I don't know much about Venus, though I should, because I think it's a more and more fascinating planet, and it's the closest to us. So we should probably study it a little more.
I mean, we seem to have a lot of water under our feet too. It just seems like water is a big part of the story of the Earth, and I'm just wondering, why one, our orbits are fairly close to one another, why one planet would end up with all of the water and another without it.
Well, because I think that the common theory is that asteroids brought water to the Earth.
That's kind of
Yeah.
being
So
displaced.
there is some of that, but I do think that the planets were born with fairly similar amount of water.
I see.
So water on Earth. So Venus lost its water, and then volcanism also releases water from the interior. We know that Venus is not nearly as tectonically active as the Earth is, and so we might be also degassing more water from the interior. The fact that volcanoes have white smoke is because it's water vapor, mostly water vapor. There's plenty of CO2 and sulfuric acid and all that, but it's mostly water. I think that's the gist. A friend reminded me that actually there is still enough water in the atmosphere of Venus that if it rained, if we made all that water rain on the surface, it would create a 30-centimeter deep ocean. So there is actually water there. There's not 4 kilometers like on Earth, but there is still water. It's not completely dry.
I don't know if you can call a 30 centimeters deep ocean, but I appreciate the
you can drown in like 3 inches of water. So
that's true.
Yeah.
So
bring your arm floaties.
Exactly, just lie very, very still. What's next for you? You have these 2 blockbuster papers that have, garnered you a lot of attention. Do you have an idea of where to go next?
I mean, the next thing is continue the observation of TRAPPIST-1. So for that, the community, I think, is hopefully gathering a little to do that. I have a project with colleagues in Belgium, in the US, in Switzerland, and also here in the UK to find more systems like TRAPPIST-1, because those planets are some of the most interesting and also probably the most typical rocky planets out there, because the type of stars like TRAPPIST-1 are the most common and they seem to produce lots of planets. So just from planet formation perspective, I think that's very important to study. I just got a renewed funding to study second binary planets more in detail, so that will carry on. And we discussed at the very beginning of our discussion about Antarctica. I think that's going to be, so while these 2 projects are, have finally matured and are entering a new phase, I think I might spend some time imagining what a new observatory in Antarctica would be, because I think we could make observations on exoplanets unlike anybody else because of how much time we would get on the telescope. So we'd be able to spend time. Most telescopes have been designed thinking, how sharp the images would be. So more in terms of size and in terms of amount of light received, but not in terms of how much time you need to observe. And I need a lot of time because we are limited by the time the planet takes to go around. And so a 2-meter is reasonable in terms of cost, and then would offer us the power of an 8-meter telescope. So we would be able to do really, really cool science with that. In addition to visiting the continent more than once, that would be absolutely wonderful.
That's very cool. I look forward to reading and hearing what comes next. I really appreciate you taking the time to guide us through all of your work and to, entertain our kind of outlandish ideas.
Well, thank you very much to you both for giving so much interest into my research and the topic widely of exoplanets. I think it's always a discussion I like having, and I'm glad that I've really enjoyed the discussion. I'm curious to see the end result and how the public will react.
Excellent. Us as well.
Yeah, and stay warm next time you go down there.
Yes,
And hopefully, we'll catch up with you down the road once this story changes even more.
Indeed. All right.
Fantastic.
Have a good day.
Have a great rest of your night, sir. Thank you for coming by.
Bye-bye.
Take care, everybody.
Bye.